And spectroscopy is basically what happens when you take light and break it up into its constituent colors. Light comes in, it's white light, hits the prism, gets spread out, becomes all the different colors of the rainbow. The sun, the earth, all of the interstellar material, all the gas and dust that goes into forming stars, all that is atoms. And atoms emit and absorb light, and that's how we see stars and planets and all these things. Say hydrogen, the most common atom in the universe. Hydrogen makes light at only very specific colors. So if you were to take the light from a star that was made entirely out of hydrogen and pass it through a prism, you wouldn't see a rainbow of colors. You'd see a bright bit here at red, bright bit at green, and a couple of bright bits at blue. So what we do with these galaxies, because they're so far away and oftentimes too faint to be seen in emission of light, is we play the trick of putting a very, very bright source behind them. So imagine you're in a swimming pool. You're sitting there in the swimming pool and you look at the end of the swimming pool is a light. And then somebody spills a cup of coffee. The color of the light is going to change because of the coffee now in the water. Well, if we replace light at the end of the swimming pool with a bright object called a quasar, maybe 10, 12 billion light years away, and we replace the coffee with our galaxies that we're looking for, what will happen is that the light from the quasar will be affected by the atoms of the gas in the galaxy. Most of the quasars I look at are 11 billion light years away. So you've got 11 billion light years worth of universe between us and that quasar for there to be galaxies along the way. So that's spectroscopy. Using these very, very distant background sources, by looking at the colors that we get from an object, we can figure out what that object's made out of, even though we can't see them in emission from the telescopes.
Right from his office at St. Michael's College, John O'Meara is exploring new galaxies 12 billion light years away. He's able to do this with the advent of scientific tools which even in today's technological world are sometimes hard to believe. The Sloan Digital Sky Survey is one of the most ambitious and influential surveys in the history of astronomy. Using an optical telescope in New Mexico, the survey has obtained deep, multicolored images of almost 1 million galaxies and 100,000 quasars. And of course, another historical event in U.S. space science was the launch and successful installation of the Hubble telescope.
The Hubble Space Telescope is arguably the most famous piece of scientific equipment since Galileo's telescope. It produces the sharpest images of objects on the sky that we've ever had. And some of the most famous images are things like the Hubble Ultra Deep Field. And this is what happens when you take the Hubble Space Telescope with an upgraded camera and you point it at one part of the sky for 2 weeks. You just say, look at one single part of the sky for 2 weeks. Do nothing but look at that. And you specifically chose a spot in the sky where there was nothing. You looked at images from the ground and you say, oh, there's nothing there. There's no stars, there's no galaxies, nothing. You turn the Hubble Space Telescope on, let it go for 2 weeks, and what do you see? You don't see nothing. To date, they've cataloged 10,000 galaxies in that image. It's one of the most important images ever taken in astronomy, because it shows that if you wait long enough and you look far enough back in time, the universe is a robust and interesting place. One of my favorite Hubble images is an image of the Carina Nebula. The Carina Nebula is a stellar nursery. Nebulae are collections of gas and dust. And whenever that gas and dust becomes slightly too dense, gravity takes over, the gas and dust collapses, and it forms stars. So this nebula is a huge collection of gas and dust. And if you look carefully at the image, you can see little spots all over the place, and that's where brand new stars are being born. Stars which are very, very big and very, very bright, much brighter and much bigger than the sun.
Cosmology encompasses everything about the universe, including the formation, evolution, and interaction of galaxies. Astronomy focuses on specific celestial bodies, including the life of individual stars and planets. Joanna Rankin is using radio astronomy to explore one type of celestial body, the pulsar.
Radio astronomers use what we would now call big satellite dishes, and the one that I've mostly used is the Arecibo Observatory in Puerto Rico, which has a mirror which is 1,000 feet in diameter, 308 meters, and that's the reflector. And it is the most sensitive radio observatory in the world. I'm Joanna Rankin. I'm a professor in the physics department of the University of Vermont. And the pulsars emit mostly in the radio. In the radio, we can detect objects that are much cooler and objects with different kinds of emission, like the pulsars that I study. Stars, as they're formed, are entirely gaseous bodies. So when we look at the sun and we think we see an edge, it is an illusion. There's a famous diagram in astronomy called the Hertzsprung-Russell diagram, and it shows that if you make a very bright star, it's going to be blue, and dim stars are going to be red. And there's a continuum of stars down through where our sun is that have different colors. That was the first big hint that there was order in the universe as far as how nature makes stars. The whole idea that stars evolve is again an idea that's only about 100 years old. And it was Darwin who gave astronomers perhaps the courage to say, well, maybe stars evolve too. We now know that the brightest blue stars, the ones that mark the constellations, have lifetimes which are not that different from the length of time that humans have been on the Earth, a few million years. And the dim ones, the sun or dimmer, have been around for times that are comparable to what we now think is the age of the universe. They have many different lifespans, and some of those big, bright, massive stars, when they die, they undergo disruptions in which the mantle of the star is ejected with great velocity in something called a supernova event. And what's left is a cinder, which is a black hole or a pulsar or a neutron star. And in the process, it develops big magnetic fields, and it also rotates very rapidly. So we're pretty sure that neutron stars, as well as black holes, are produced in the evolution of massive stars. These pulsars are a very late stage in the evolution of stars. They're about the size of a city, but they have as much material as the sun, so they have enormous density. If I reach down to pick up 1 cubic centimeter of this star stuff that a pulsar is made of, I'd have to exert myself to lift about 1 billion metric tons, which I think is over the top of my strength. So anyway, they have a number of very interesting phenomena. Their diameter is 10 miles. They rotate rapidly, typically once a second, but they can rotate up to about 1,000 times a second. In that rotation, there is enormous stored energy. My interest in these stars is what makes them go? How do they work? There are a few astronomical objects that have scales of change, if you like, on the order of a human heartbeat. Here's one that plays a program that is about once a second, typically. Some of the most exotic physical conditions in the universe. They have the strong gravity, they have enormous electric potentials. I mean, lightning on Earth is piddling compared to what a pulsar can generate. The magnetic fields on a pulsar are a million times bigger than the Earth's magnetic field. So you put all of those three things together and you have physical conditions that couldn't be generated for a millisecond in any physical laboratory. So we try to understand how they work, and we also try to understand our basic understanding of physics.
One of the great things about being an astronomer is that you can always link whatever you're doing in astronomy, however far-fetched and weird, be it cosmology, be it black holes, be it quasars, gamma ray bursts, you can always link that back to the question of why are we here on Earth at all, right? How did it get to be that there could be intelligent life sitting around contemplating the universe? And so while cosmology doesn't explicitly ask the question, are we alone in the universe? What cosmology has told us is that our place in the universe here on the Milky Way galaxy is not unique. So it would be somewhat arrogant for us to think that we are unique, at least in terms of living creatures on planets. I do think that cosmology and astronomy put together make a very strong argument that we're not alone in the universe, that it's a fun thing to think about, and that it's not a silly thing to think about. Every piece of evidence that we've got makes us think that it's a completely reasonable hypothesis.
The number one thing we got from Apollo was the raised consciousness and spirit of human beings, not just Americans, but particularly Americans, but all over the world, of what humans could do if they wanted to, how great they could be if they wanted to. They could actually achieve an impossible dream.
The most profound impact on me, and it's the same on many, many of the astronauts and cosmonauts, is that you get a chance to get away from the Earth and look back at it and see how beautiful it is and how small it is in the vastness of space. And you've seen the Earth just as a beautiful blue, white, and green marble. If the Earth were an apple, the atmosphere would probably be not much bigger than the thickness of the apple skin. And suddenly you turn into an environmentalist. You are very, very impressed with the fragility of our environment and how important it is that we take care of it.
I think we'd be a better planet, humans would be better, if we had more of this spirit of exploration, whether it's unmanned spacecraft, whether it's looking at somewhere in telescopes, but looking out and trying to be more than we are on a day-to-day basis. We need that spirit in our hearts. Not everybody has that spirit, or not everyone can get that spirit.
As early peoples gazed at the stars to pose spiritual questions, modern humans have lifted their spirits by literally walking on the moon. Those that have been to space describe the delicate planet Earth that they look back upon with awe and newfound reverence. Some would argue that we aren't putting enough energy, time, and resources into deepening our understanding of space. Nonetheless, whether our future has us walking on Mars or inhabiting other planets, we'll continue to be awed by the magnitude of the universe as it drives our search for meaning. I'm Amy Seidel. Please join me next time for more emerging science.
We're go for main engine start. We have main engine start. 4, 3, 2, 1.
Endeavor, go at throttle up.
Go at throttle up.